Welcome. Today, we're diving into the fascinating world of transfer learning in artificial intelligence. If you've ever wondered how AI models can learn faster and perform better with less data, transfer learning is the secret sauce. In this video, we'll break down what transfer learning is, why it matters, and how it's transforming the field of AI. We'll also look at real-world examples and the science behind this powerful technique. Let's get started by understanding the basics of transfer learning and how it fits into the broader landscape of machine learning. Transfer learning is a machine learning technique where a model developed for one task is reused as the starting point for a model on a second, related task. Instead of training a model from scratch, which can be time-consuming and require massive amounts of data, transfer learning leverages knowledge gained from previous learning experiences. This approach is especially useful when you have limited data for the new task, but access to a pre-trained model that has already learned useful features from a large dataset. Transfer learning is a game changer in AI because it dramatically reduces the resources needed to train effective models. By building on existing knowledge, AI systems can adapt to new tasks with less data and computational power. This is particularly important in fields where labeled data is scarce or expensive to obtain. Transfer learning enables faster development cycles, improved performance, and opens up AI to a wider range of applications, from healthcare to finance and beyond. At its core, transfer learning involves taking a model that has already been trained on a large dataset, like ImageNet for images or Wikipedia for text, and fine-tuning it for a new but related task. The model's early layers, which have learned general features, are kept, while the later layers are retrained to specialize in the new task. This process allows the model to quickly adapt and perform well, even with limited new data. The concept of transfer learning is inspired by the way humans learn. We often apply knowledge from one area to solve problems in another. For example, once you learn to ride a bicycle, picking up how to ride a motorcycle becomes easier. Similarly, AI models can transfer what they've learned from one domain to another, making them more flexible and efficient learners. Transfer learning comes in several forms. The most common is inductive transfer, where the source and target tasks are different but related. There's also transductive transfer, where the tasks are the same but the domains differ, such as applying a model trained on English text to French text. Finally, unsupervised transfer learning deals with transferring knowledge when neither the source nor the target task has labeled data. Inductive transfer learning is the most widely used type. Here, the source and target tasks are different, but related. For instance, a model trained to recognize animals in photos can be adapted to identify specific breeds of dogs. The model's general understanding of animal features helps it quickly learn the new, more specific task. Transductive transfer learning is used when the source and target tasks are the same, but the data domains are different. For example, a sentiment analysis model trained on movie reviews in English can be adapted to analyze reviews in Spanish. The underlying task, sentiment analysis, remains the same, but the model must adjust to the new language domain. Unsupervised transfer learning is a bit more complex. Here, neither the source nor the target task has labeled data. The model learns patterns from the source domain and applies them to the target domain, often using clustering or representation learning techniques. This approach is valuable when labeled data is unavailable or too costly to obtain. One common method in transfer learning is feature extraction. Here, the pre-trained model's layers are used as a fixed feature extractor. The output from these layers is fed into a new classifier, which is trained on the target task. This approach is efficient and often yields strong results, especially when the source and target tasks are closely related. Fine-tuning is another popular approach. Instead of keeping the pre-trained layers fixed, you allow some or all of them to be updated during training on the new task. This lets the model adapt its learned features to better fit the specifics of the target data, often resulting in even better performance. Transfer learning has revolutionized computer vision. Models like VGG, RaiseNet, and Inception pre-trained on massive datasets like ImageNet, can be quickly adapted to new image classification tasks. This has made high-performing vision models accessible to researchers and developers with limited data or resources. In natural language processing, transfer learning has enabled breakthroughs with models like BERT, GPT, and RoBERTA. These models are pre-trained on vast text corpora and then fine-tuned for specific tasks like sentiment analysis, question answering, or translation. The result is state-of-the-art performance with less labeled data. Speech recognition systems also benefit from transfer learning. Models trained on large speech datasets can be adapted to new languages or accents with minimal additional data. This flexibility has accelerated the development of robust voice assistants and transcription services. Healthcare is another field where transfer learning shines. Pre-trained models can be fine-tuned to detect diseases in medical images, such as X-rays or MRIs, even when labeled data is scarce. This has the potential to improve diagnostic accuracy and make advanced medical AI tools more widely available. In finance, transfer learning helps models adapt to new markets or financial instruments. For example, a model trained to predict stock prices in one market can be fine-tuned to work in another, leveraging its understanding of financial patterns. This adaptability is crucial in the fast-moving world of finance. Robotics also benefits from transfer learning. Robots trained in simulation environments can transfer their learned skills to real-world tasks, reducing the need for extensive real-world training. This approach accelerates the development of intelligent robots capable of adapting to new environments and challenges. Recommendation systems, like those used by streaming services or online retailers, use transfer learning to personalize suggestions. By leveraging models trained on large user datasets, these systems can quickly adapt to new users or products, improving recommendations and user satisfaction. Autonomous vehicles rely on transfer learning to adapt driving models from one environment to another. For instance, a self-driving car trained in one city can transfer its knowledge to navigate a new city, adjusting to different road layouts and traffic patterns with minimal retraining. Gaming AI uses transfer learning to create smarter, more adaptable agents. Models trained on one game can be fine-tuned to play new games, leveraging their understanding of game mechanics and strategies. This leads to more challenging and engaging gameplay experiences. Transfer learning offers several key benefits. It reduces the need for large labeled datasets, speeds up model development, and often leads to better performance on new tasks. By reusing knowledge, AI systems become more efficient and accessible, enabling innovation across industries. Despite its advantages, transfer learning comes with challenges. If the source and target tasks are too different, the transferred knowledge may not be useful, or worse, it could hurt performance, a phenomenon known as negative transfer. Selecting the right pre-trained model and fine-tuning strategy is crucial for success. Negative transfer occurs when the knowledge from the source task actually impairs performance on the target task. This can happen if the two tasks are unrelated or if the model overfits to the source data. Careful selection of source tasks and regularization techniques can help mitigate this risk. Choosing the right source task is critical for effective transfer learning. Ideally, the source and target tasks should share underlying features or patterns. For example, using a model trained on general object recognition for a specific animal classification task works well because both involve visual features. Pre-trained models are widely available for many domains. In computer vision, models like RayNet and Inception are popular choices. In NLP, BERT and GPT have become industry standards. These models are often open source, making it easy for developers to leverage transfer learning in their projects. A typical transfer learning workflow involves selecting a pre-trained model, adapting its architecture if needed, and fine-tuning it on the target dataset. This process is iterative, often requiring experimentation with different layers, learning rates, and data augmentation techniques to achieve the best results. One of the biggest advantages of transfer learning is its ability to work with smaller datasets. Since the model has already learned useful features from a large source dataset, it can achieve good performance on the target task with much less data. This makes transfer learning ideal for applications where data is limited or expensive to collect. Data augmentation techniques, such as rotating or flipping images, can further enhance transfer learning. By artificially increasing the diversity of the training data, these techniques help the model generalize better to new examples, improving its robustness and accuracy. Domain adaptation is a special case of transfer learning where the source and target domains differ, but the task remains the same. Techniques like adversarial training can help models bridge the gap between domains, making transfer learning even more powerful in real-world scenarios. Multimodal AI systems, which process multiple types of data like images and text, also benefit from transfer learning. Pre-trained models for each modality can be combined and fine-tuned together, enabling richer and more flexible AI applications. Edge AI refers to running AI models on devices like smartphones or IoT sensors. Transfer learning allows these devices to use compact, fine-tuned models that perform well with limited computational resources, making AI more accessible and responsive at the edge. Federated learning is a decentralized approach where models are trained across multiple devices without sharing raw data. Transfer learning can be used to initialize models on each device, speeding up convergence and improving performance while preserving privacy. Continual learning is about enabling AI models to learn new tasks over time without forgetting previous ones. Transfer learning provides a foundation for continual learning by allowing models to build on existing knowledge, making them more adaptable and resilient. Meta-learning, or learning to learn, is closely related to transfer learning. In meta-learning, models are trained to quickly adapt to new tasks, often by leveraging transfer learning techniques. This enables AI systems to become even more flexible and efficient in handling diverse challenges. As transfer learning becomes more common, understanding how and why models make decisions is increasingly important. Explainable AI techniques can help shed light on which features are being transferred and how they impact the model's predictions, building trust and transparency. Fairness is a key concern in AI. Transfer learning can sometimes propagate biases from the source data to the target task. Careful evaluation and bias mitigation strategies are essential to ensure that transferred knowledge does not lead to unfair outcomes. Privacy is another important consideration. When using pre-trained models, it's crucial to ensure that sensitive information from the source data is not inadvertently transferred. Techniques like differential privacy can help protect user data during transfer learning. Transfer learning is widely used across industries. From automating customer service with chatbots to improving product recommendations and optimizing supply chains, transfer learning enables businesses to deploy AI solutions faster and more effectively, driving innovation and growth. In research, transfer learning allows scientists to tackle new problems with fewer resources. By building on existing models, researchers can explore novel applications, test hypotheses, and push the boundaries of what AI can achieve, even with limited data. The future of transfer learning is bright. As AI models become more sophisticated and datasets grow, transfer learning will continue to play a central role in making AI more accessible, efficient, and powerful. We can expect new techniques and applications to emerge, further expanding the impact of transfer learning. Lifelong learning is the idea that AI systems should continuously learn and adapt throughout their existence. Transfer learning is a key enabler of this vision, allowing models to accumulate knowledge over time and apply it to new challenges as they arise. Transfer learning not only makes AI smarter, but also enhances human-AI collaboration. By quickly adapting to new tasks, AI systems can better support human decision-making, automate repetitive work, and unlock new possibilities across professions. Transfer learning is helping democratize AI by lowering the barriers to entry. Smaller organizations and individuals can now build powerful AI solutions without massive datasets or supercomputers, making AI innovation more inclusive and widespread. To sum up, transfer learning is a powerful technique that allows AI models to leverage existing knowledge for new tasks. It reduces data requirements, speeds up development, and enables AI to tackle a wider range of problems. As AI continues to evolve, transfer learning will remain a cornerstone of intelligent, adaptable systems. Thank you for joining us on this journey through transfer learning in AI. We've explored its definition, types, benefits, challenges, and real-world applications. As you continue to learn about AI, remember that transfer learning is a key tool for building smarter, more efficient, and more accessible models. Stay curious and keep exploring the world of artificial intelligence.